All right. So we're going to start our organic unit formally, and we're going to start by talking about homologous series and some properties therein. Okay. So a homologous series, let's start off by defining it. It's a set of compounds that differ by a CH2 group, meaning that we're adding in a carbon and 2 hydrogens each time. So methane, ethane, propane, butane, pentane, etc. And we're going to see that they have similar chemical properties, but trends in their physical properties. So things that you need to know about homologous series, like if you're asked to define it, same general formula or differ by CH2 group, same or similar chemical properties, but a trend or a gradation in physical properties. Real quick, I want to note that they don't always have the same empirical formula because that's just not how the numbers work, but they do have the same general formula. Okay, so all of our physical properties can be traced back to intermolecular forces. So a quick review. Your London dispersion forces are caused by the movement of electrons. Remember that there's an instantaneous dipole that then induces dipoles in neighboring molecules, and that these are really only significant in your nonpolar molecules. Also remember that as molecular size increases, these particles become more polarizable, and so the London dispersion forces increase. Dipole, remember that these are in all polar molecules, and it's the attraction between a slightly positive region of one molecule and a slightly negative region of another molecule. And then lastly, your hydrogen bonding. You've got to have hydrogen, and it's got to be bonded to an electronegative atom, such as oxygen, fluorine, nitrogen, with a lone pair on it. And because that bond is very polar, and because hydrogen is very small, the positive or the slightly positive hydrogen of one molecule is going to be attracted to the very negative lone pair of electrons that are on that region, that functional group in a neighboring molecule. And remember, water forms hydrogen bonds. Okay, so if we talk about which various functional groups are polar versus nonpolar or polar with hydrogen bonding, we get these. So your hydrocarbons that are just straight hydrogen and carbon, hence hydrocarbon, are all nonpolar. So all they're going to have are those London dispersion forces. Your polar molecules so there's dipole, but there's not any hydrogen bonding, would be your ethers, your halogenoalkanes, your ketones, and your aldehydes. So notice that yes, there's hydrogen and oxygen in an aldehyde, but the hydrogen is not bonded to the oxygen, so it's just polar. But these guys, your alcohols, carboxylic acids, amides or amines, and your carboxyamides are all going to form hydrogen bonding. So they're going to have the strongest intermolecular forces, and we're going to see different trends with them. Okay? So, there are some other effects on intermolecular forces. The molecular weight and the increased branching. So with molecular weight, we already said this with London dispersion forces, but increased molecular weight means increased polarizability, I don't know how you would say that. Imagine it with a British accent, it kind of sounds funny, and branching. So take a look at these. These are pentane, 2-methylbutane, and 2,2-dimethylpropane. So these are all C5H12. But these pentane molecules are going to pack very nicely together with each other, so just because they're close to each other, the intermolecular forces are going to be stronger than these guys, the 2,2-dimethylpropane. This is not going to pack very well together, so there's greater distance between the molecules, which means they have weaker intermolecular forces, and we can see that with their boiling points. Okay, remember that in order for something to boil, we have to completely overcome the intermolecular forces. Okay, so volatility is your science word for boiling point, and it's affected by the length of the carbon chain, because as the molar mass increases, the London dispersion forces increase, which means the boiling point increases since we have to overcome those. And then we already said this, but the branching. Okay, more branching equals less intermolecular force, which means lower boiling points. And so then you have a little summary chart at the bottom of that page. Okay, we're going to show you some trends and some patterns with this as we go through this, but you need to think through who's polar, who's not, da-da-da-da. Okay, our other physical trend is solubility, and we're talking about solubility in water. So these are all determined by the polarity. So alkenes, and alkynes, well, they're all nonpolar. They are not going to be soluble in water. They would be soluble in other nonpolar solvents. Remember, like dissolves like. And the larger the alkane or the alkane chain, the lower the solubility. But the more polar the compound, the more soluble it is in water. Okay, so let's take a look at these two alcohols. We have ethanol and hexanol. Okay, so here's ethanol, here's hexanol. Well, both of them have this polar alcohol group that can form hydrogen bonds, but their solubilities are very different. Why? Well, look at how much of hexanol is nonpolar. So it's just got the itty-bitty polar region. And so it's slightly soluble in water, but really not very. And then here, if you look at this as a proportion of the molecule, well, a larger portion of it is polar, so ethanol is soluble in all proportions. Okay, so all things else being equal, like same functional group, the longer the carbon chain, the less polar it is. Okay, take a minute and think about this question, and pause the video, and when you're ready to take a look at it, I'll show you the answer. All right, so which of these has the lowest boiling point and why? So if we look, these are all the same or very similar empirical formulas and molar masses. And we do have ether right here, but what you should see are branches. Okay, so this would be 2-methylbutane, so we have our butane and then we have our methyl group. This is 2,2-dimethylpropane, so here's our central carbon and the 4 methyl groups coming off of it. Just straight up pentane. And our ether. Sorry about the Roman numeral, that's the best picture I could get from it. So, which one of these is going to have the lowest boiling point? Well, it'll be the one with the weakest intermolecular forces, which is going to be B, because it has the most branching and it's nonpolar, so it's got the weakest intermolecular forces. All right, there you go for your homologous series.